Okay, folks, welcome back. We're going to talk a bit about reciprocal functions today. So we've learned before what a reciprocal is. So for example, if you've got a number like 3/4, the reciprocal of it is basically going to be the flipped version. Okay, so these are going to be numbers that are flipped. Now, this is a little bit different than the inverse, and we'll talk about the inverses later, but if we're going to deal with a reciprocal, you're literally just going to flip over what you see. So that number 3/4, its reciprocal will then be 4/3. Okay, flip that numerator to the denominator, vice versa. So if it's 2x, the flipped version of that is going to be 1/2x. Since remember that if it's 2x, I can always divide it by 1, so I do technically have a denominator here that we could flip. Now for this last one, I can clearly see a numerator and a denominator, so we're going to switch the places of them. So my reciprocal is going to be 3/x² minus 9, and I've got the flipped version now. But as these get a little bit more complex, we're going to see those graphs become a little bit more complex as well, and we're going to analyze what happens to those pieces. So let's start with an easy case. Let's start with the regular old graph y equals x and its flipped version, and we'll see what happens. So we'll plot some ordered pairs that form x, y, draw the curve using the points. Okay, so we'll pick some values for x, get their y values, and then we're going to flip those x values to see what happens for the reciprocal graph. So given the starting point is 0. Now, you can choose any x values you want. I chose to just work with my whole numbers here. All the way up to 4 in both the positive and negative directions, just for ease. Now you can see that if my graph, my equation is y is equal to x, all of my y values have to match all of my x values. That's what that says. Now for my reciprocal graph, y is equal to 1/x. So whatever my x value was, we're going to flip that over, take its reciprocal for our y value. Okay, we're going to take all of those and flip them over. So we're going to have values of -1/4, -1/3, -1/2, -1. Now, when I get to 0, if I try to take the reciprocal of that, it will then tell me I have 1 divided by 0. That gives us a problem. I can't actually do that division. I actually get an error, which is divide by 0. So this one technically doesn't exist. Okay, now that's interesting. Now, if I take the reciprocal of 1, I still have 1. That's also interesting. And you can see the same thing happened with -1. If I try to take the reciprocal of -1, it will then tell me I have 1/-1, which is the same thing. So that is interesting. Let's just keep that in mind until we can actually put that into words. Okay, if I do 2, then I'm going to get 1/2, 1/3, and 1/4. So there's all my values in blue that we're going to try and graph. I've got all of their x values in black. We're going to go plot some points. So let's do the original one first. So one of my points was 0, 0, then 1, 1, 2, 2, 3, 3, 4, 4, and -1, 1, and the pattern continues. Now, since this is linear, I'm actually able to connect them with a line. And if it is a line, that line should have arrows on the ends indicating it actually goes on continuously forever. So there's my original one. So let's call that y equals x. Now we're going to go ahead and start plotting some points for our reciprocal function. Now, I'm going to start by plotting these two 1s first, so both positive and -1. It gives me some idea of where my graph is going to be. So when x is -1, my reciprocal y should also be -1. Okay, so you can see that we've got a point that overlaps. So I'm going to have another one that overlaps as well. So those points don't vary from original to reciprocal. That's important. We're going to go graph the other ones as well, just to give us kind of a shape to see what happens. So when x is -4, my y value is -1/4. And that might be a little challenging to graph on here, so we'll do our best to try this. So when x is -4, -1/4 might roughly be here. Let's do let's just keep going. -3 and -1/3. So -3, -1/3, a little bit closer to halfway. -2 is a halfway. So it's kind of hard to see since we're so zoomed out, but it looks like each point is getting a little bit smaller. So we kind of have the beginnings of a curve going on here. Okay, so there's our 4 points. Now we can't actually place a point when x is 0. There's no point that exists along this line. Okay, so that's important. Now we can move on to our 1. So we plotted that 1 already. 2, 1/2 is our next point. So 1, 2, 1/2 would be roughly here. Then 3 should be 1/3. And 4 is 1/4. So you can see now, I've kind of got 2 differing curves here. On the left side of that y-axis, I have a downward facing curve, essentially, if I were to keep going and putting some more points. On the other side of that y-axis, it looks like my curve starts to go upwards. So you can kind of see that being formed. Now, if there's no point along this y-axis, we said when x is equal to 0, there isn't a point there. But what happens when x is equal to, let's say, 0.5? Well, if in my original graph, if x was 0.5, I should have a y point at 0.5. So there should be something that happens here because y is equal to x. So if x is a half, y should also be a half. I should have a point that exists there. Okay. Now, since there's nothing in the middle, I can get as close as I want to this without actually ever touching it. So I could kind of draw the shape here because I know the general shape. It's not perfect, but I could start to draw something. Now, I don't know if I'm going to cross all of my points exactly, but I know I can keep going and going and going and get closer to that x equals 0 mark without ever actually touching it. The same is true for the other side. Okay. So here you can start to see that these reciprocal graphs look a bit strange. They've got some different pieces going on, and we're going to talk about all the pieces and all of that, so don't worry. But if you're unsure how the heck this graph is supposed to go in those directions, let's think about this. So if we say that our function f of x is equal to 1 over x, that was our reciprocated version. Let's imagine that we pick some numbers for x and see what happens. So let's say that we let x be equal to 0.0001, so some very small value. Okay, so that means I can take this x value, plug it into this equation, get a y value out of it. So let's try just that. 1 divided by 0.0001, and that will give me an f of x value equal to 10,000. So that is very large. So this graph only goes 1, 2, 3, 4, 5, 6, 7. Only goes up to 7. So if I'm really, really close to that y-axis, x is very, very small, my y value actually shoots all the way up to 10,000. That's interesting. If I pick a very, very small x, I get a really, really big y value. What happens if I pick a very, very big x? So let's say that we let x equal 100,000. Okay, that means that my function would have a value then. It should, in theory, be something very, very small. That might be one too many. 100,000, yeah. 1 times 10 to the power of -5. So I have 5 zeros, and then I've got a 1 after. So very, very tiny. 0.0001. Okay, so there's my actual value this time. So if my x was really, really large, my y is actually very, very small. So I am getting very, very close to that x-axis. Now, if I would have chosen an x value of 1,000,000, I would have 1 times 10 to the power of -6. I'd be getting magnitudes closer to that x-axis, but again, wouldn't actually ever touch it. Now, what happens in the middle here? If I pick a number really, really, really close to 0, we saw that I got really, really close to that y-axis. Now, the same would be true on the other side if I were to choose negative x's. The same thing would happen. But I wouldn't actually ever get to it. I could probably get to 0.000000001 on something really close, but again, wouldn't actually ever cross it because I can't exist at that point. So that's important. So let's go make a couple of notes here. Now, we can see that, maybe change the color. So the reciprocal can't spell today. Reciprocal. Okay, so their reciprocal has an undefined point when x is equal to 0. Okay, so if I have something that's undefined here, remember back to when we talked about rational expressions. That meant I had a non-permissible value. Okay, so there's an NPV here from the rational expression. Okay, and that non-permissible value came from that denominator, which in fact was the original function. So if there's a value in that original function that makes that y-coordinate equal to 0, that's going to give us an issue when we go to take the reciprocal, because I can't really reciprocate 0. That will essentially give me a value where I can't have anything. It doesn't exist there. So that's interesting. The other thing you can think about is here in this example, when x is equal to 0, that is the x-intercept of the original y is equal to x. So wherever that line crosses that x-axis, if I try to flip it over, I'm trying to flip over 0, which I can't do. That's interesting. Now, I am also asked to determine the points of the graph where the graph y equals x intersects with the graph y equals 1 over x. Now, if you notice, there should be 2 spots where that happens. I've even circled them. They were the first 2 points we plotted. They were where the original function was equal to -1 and +1. Those 2 points were the same on the reciprocal graph. Okay, so that means those 2 points are the intersection points of those 2. So the points, and this would have been 1, 1, and -1, -1 are intersection points of these equations. Okay, those points didn't vary from one to the other, and for that reason, we call them invariant points. So these are invariant points, okay, since they do not vary. Now, the value of them doesn't vary. Okay, so the y-coordinate is going to be always at -1, +1. The placement of them might be different. They're going to be somewhere along those horizontal lines of -1 and +1, which I'll put in purple for you. Okay, so my invariant points will be somewhere along those purple lines, but as you can see, the x-coordinate could change. And we'll do a couple of examples down below that will illustrate that. So that might change, but they'll always be along those purple lines. And that's interesting. That's kind of cool. Okay, so those are my invariant points. Now, we could also say that my original function f of x is going to have invariant points when it's equal to the values of positive or -1. So remember that f of x really is the same thing like saying the output of your function. So if y is equal to f of x, remember x is the input, f of x is what we get as the actual value. When the f of x is equal to positive or -1, we could find the corresponding x values to make that true. Okay, so this is an important fact that we're going to use throughout this to find those invariant points. So that's important. Okay, if we turn this, we have a little bit of a cheat sheet when it comes to some of the aspects of these reciprocal functions. So the first bullet there says, when the value of the original function is 0. When the value of the original function is 0, the value of the reciprocal function is non-existent or undefined. And what we call an asymptote exists. This word refers to the line that it can't cross. So if here's my reciprocal function from before, the line it couldn't cross was x is equal to 0. Okay, that y-axis, we give it a name and we call it an asymptote. Now you can see here that there's also another horizontal line which it can't cross, the x-axis. So I could potentially have horizontal asymptotes as well as vertical asymptotes, and we'll come up with a way to how we find them and distinguishing between the two. So I could have an asymptote. All this means is my reciprocal function will not cross that line. Okay, it's bound to be on the other sides of it. Okay, so this would be the x-intercept of the original function, and it represents the non-permissible value of the reciprocal. Okay, so those values will change depending on the original function, or the reciprocal if you're working backwards. Where the values of the original function are. So when the values of the original function are increasing, okay, the values of the reciprocal function does the opposite. It decreases. Okay, so that's decreasing. If the original function is decreasing, then that means the reciprocal version is doing the opposite. That means it's increasing. Okay, when the original function has a value of 1 or -1, so not the x, this is talking about the y. So this is talking about y or f of x, the actual value, the output. So when the original function is 1 or -1, this point will exist on the reciprocal graph as well. Because this point does not change, we call it an invariant point. Invariant point. Okay, it's a point that's on both graphs, original and reciprocal. When the value remains approximately the same as x goes towards infinity or -infinity, the reciprocal will approach what we call the horizontal asymptote. Okay, and an important note, which I'll add in here, we're only going to focus on functions. So we will focus on functions of the form a over f of x. So some number on top, could be 1, could be another constant like 2 or 3, divided by the original function f of x. Okay, so this is the form we're going to focus on for reciprocals. Now, since our numerators are just a constant, okay, so since a is a constant, our only horizontal asymptotes will be y is equal to 0. Okay, so I could potentially have other scenarios where my horizontal asymptote isn't the x-axis, but that comes later when we deal with different degrees of polynomials top and bottom. We're only going to focus on this case for now, and I've got a number on top. Since the degree of the bottom will be larger than the degree of the top, think of this like having x to the power 0 on top, which is going to give us 1 or just a constant, and some other degree on the bottom. Since the degree of the bottom is larger, we're going to only have horizontal asymptotes of 0. So basically every time you can think about that, it'll only be our vertical asymptotes that are going to change. and they come from the non-permissible value. So in this first example, it asks us to identify some asymptotes, and we're asked to determine the equation of the vertical asymptote of the reciprocal function of f of x equals negative 5x plus 4. So we're taking our original function, which is f of x, and we're turning it into its reciprocal function, 1 over f of x. Okay, so that means we need to find the non-permissible value of the denominator. So we need to figure out where negative 5x plus 4 is actually equal to 0. If I can do that, I've got my non-permissible value. So we're just going to solve for x. Minus 4 from each side. So negative 5x is equal to negative 4. Divide both sides by that negative 5 coefficient on x, and you will see that x is equal to 4/5. That's going to be the value that makes this original function equal to 0. That's also going to mean that's the value that makes our denominator 0. This is the value that gives us that asymptote which we can't cross. Okay, we can even graph this in our calculator just to see what they look like. So y equals 1 over, in brackets, negative 5x, that was plus 4, and we'll close that and hit graph. Now, these graphing calculators, while they are good, there is an issue when we work with the window settings. So let's just zoom in on that point somewhere close. Okay, and we can see a couple things. So we can see right here that I've got a vertical line that goes up and down through this, and I can see the two parts of my reciprocal function like we graphed them before. Now, this calculator is not perfect. What it does is try to draw one line to continue everything, but for you, you can critically think, now that vertical line shouldn't be there. Okay, that vertical line is the asymptote. Okay, so it won't actually be there on the graph. It just shows up in the calculator. It's just a flaw when you go to graph things with it. So just be careful and aware of that, that vertical asymptote, that vertical line shouldn't be there on the graph. Okay, you can see your horizontal asymptote right of 0. But there's what our graph would look like. Now let's go try to do this by hand. So we're going to try to sketch the graph of this, 1 over negative 3x plus 6, and determine its domain and range. So it's helpful to find some of these key points and key aspects of the graph first before we go to try to draw something. So let's find the vertical asymptote first. So our vertical asymptote comes from the non-permissible value of the denominator. So if negative 3x plus 6 is that original function, let's find the value that makes it equal to 0. So that means that negative 3x should be equal to negative 6, x should be equal to 2. So there's our vertical asymptote of 2. Now when we go to, I'm going to include it on this graph, but I'm going to include it using a dotted or dashed line. Okay, so this just gives us an idea of where that actually is, just so we know we can't actually cross it, just like here. Okay, so there's our vertical asymptote. The other things that are going to be helpful is to figure out which points are the same on the original and the changed graph. So we need to find the invariant points. Invariant points. And again, those points happen when I'm equal to positive or negative 1. Now this is the y value equal to it, and it's the y value of the original, because I could make it equal to the reciprocal, but then I have to deal with fraction. So dealing with the original is actually easier. So we're going to figure out what x is when y, or my function, f of x, is equal to 1, or it's equal to negative 1. The values for x will tell me where along that horizontal line I have to be. So let's solve for x in the first part. So minus 6 from both sides, that means negative 3x is going to be equal to negative 5. So that means x is equal to 5/3. Therefore, my invariant point is at 5 over 3, comma 1. Underneath, if I do the same thing, that means negative 3x is going to be equal to negative 7. So x is going to be equal to 7 over 3. Therefore, 7/3, comma, negative 1 is my other invariant point. Now we're going to go plot those. Now it won't be perfect, but it will give us a slight idea of where these are. So 5 over 3 is roughly 1.7. So do your best estimate as to where that goes. So if that's 1.5, 1.7, somewhere there, and remember that that y value of that point should be 1. So there's one of my points. We're going to plot the other one as well. Now 7/3 is just under 2.5 for x. So here's 1, here's 2. I know I can't be there, about halfway roughly, and then -1. So I should be right around here. And again, not perfect, but it does get us somewhere in the right area. So those invariant points are on opposing sides. If I were to draw my original one, that's linear with a negative slope and a y-intercept of 6. So 1, 2, 3, 4, 5, 6. Somewhere here would be that original point. So pink is on the original. Now you can see that those 3 points roughly form a straight line. Now again, it doesn't look perfect just because of the way we've drawn it, but if I did draw it in there, I would have a linear function going straight through those 3 points. So let's go finish up drawing our reciprocal. Now we said if it is of this form and I've got a 1 on top, that means I actually have a horizontal asymptote as well. So HA, horizontal asymptote, BA, vertical asymptote. My horizontal asymptote will just be my x-axis, and that means that y is equal to 0. So technically, I should have another asymptote here, straight through, where y is equal to 0. Okay, so there's my other asymptote. You can even label them as horizontal and vertical if you like. But now this basically forces me to draw my graph. Now, I'm bounded by the regions that the asymptote breaks this graph into. So I basically only have one way to draw the graph that goes through these points. I basically am going to have a couple of u's reflected or turned, however you want to think about them, that get really, really close to each asymptote, but don't actually ever cross them. Now, it's hard to draw it. And again, it doesn't have to be perfect. We just need the shape. But you can see that I am going to get very, very close on both sides. So towards that x-axis and towards that vertical asymptote. Okay, and even if I try to graph it in here as well, you can see that it should look somewhat similar. I'll zoom out. Maybe I don't need to. So there's roughly 2 where we said it would be. Here's my horizontal asymptote. Let's see what happens if I do go back to normal. Okay, so you can see it. Now it doesn't go all the way up. It's just a flaw, again, of the graph. It should be going all the way up to infinity because it should go on forever, getting infinitely close to that value of 2 on the x side of things. But you can see the similar shape. So it kind of looks like a heartbeat in here. Okay, but there's my graph. We are also asked to determine the domain and range. Now, since I've got a couple breaks in the graph, this changes how I'm going to write the domain and range a little bit. Now let's move some stuff here so I have a little bit of space. Okay, so let's talk about domain first. Now, domain was the set of all of the possible x values. So if I start way on the left, I'm basically coming in from an x value of -infinity. And I am going to have values there for y all the way up until I get right up against that vertical asymptote. So there's going to be 2 distinct intervals for this domain. Coming in from -infinity is where we're going to start. So I can have an open bracket with -infinity. That open bracket tells me I can't actually have that as a value. And I'm going to go all the way up until x equals 2. Now, since I can't actually have the value of 2, I have to have an open bracket there as well. Okay, so this is interval notation like we've learned before for domain and range, but now I have to account for the other side of that interval on the other side of 2. So we're also going to say that I have another interval, which is 2, and again, open bracket, but now that x, all those x values go all the way out to +infinity. Close the bracket. So here's my domain. I come in from -infinity. I have a brief pause at 2 where I can't actually get to it. And then we continue on from the other side of 2 all the way to +infinity. Now, I can't ever have those square type brackets because I can't actually include 2 in the domain. I have to make sure it's separated with those round brackets. But other than those restrictions, x can really be any real number. Okay, the range is going to work quite similar. So let's do that maybe a different color. So for the range, let's think about this in terms of y, so top to bottom. So we'll start down below. Now this arrow tells me I can keep going, so I'm going to come in from negative infinity, open bracket again. Now I keep going all the way up until I hit that y value of 0, which I can't have. So I stop at 0, open bracket. My second part is when I'm on the other side of 0. So we'll start at 0 again, go all the way to positive infinity, all the way up. But I can't ever have those square brackets on that 0. But y could be any other value. Okay, so there's my domain, there's my range. I just have to think about 2 parts to this graph now, rather than 1 interval. Okay, I do have 2 intervals that are not continuous anymore, they're broken. I've got to think of both parts, but there's my graph. For B, let's try to sketch this one as well. Very similar questions, just different functions. So we'll try to find that vertical asymptote again. So our vertical asymptote comes from the denominator of the reciprocal. So x plus 1, if it's equal to 0, that means that x equals negative 1 is our vertical asymptote. Okay, that's very helpful. We can go find some invariant points as well. We can even state our horizontal asymptote at this point is going to be y equals 0, just like all of the other ones. Since there's a constant on top, that will be y equals 0. Okay, let's go find our invariant points. So invariant points when f of x is equal to 1, positive or negative 1, let's say. Okay, so that means x plus 1, that's f of x, has to be equal to 1, or f of x is equal to negative 1. These are my 2 cases. If it's equal to positive 1, that means that x is equal to 0. Therefore, my point is 0, 1. If it's equal to negative 1, that means x is equal to negative 2. That means my point is negative 2, negative 1. Okay, and like I said before, the y values will stay as 1 and negative 1, but the placement of them along those horizontal lines will be different. One of them is going to be at 0 this time, one of them is going to be at negative 2. With the 2 asymptotes, with the 2 invariant points, we have enough information to draw this graph. So let's go try to put some information on here. So I've got a vertical asymptote when x is equal to negative 1. So there's x equals negative 1, can't cross that. Got a horizontal asymptote when y equals 0, can't cross that. Now, if the placement of these points is going to be important. So 0, 1, there's one of them. Negative 2, negative 1. So negative 2, negative 1 is down here. And there you have it. I've got my invariant points. I'm bounded by those asymptotes. There's only one way to draw this. Okay, I'm going to approach each asymptote all the way. And again, I am going to have those arrow tips on there. There's only one way to draw this. Okay, we can do the domain and the range as well. So let's say our domain, we'll keep it with the same interval notation. So we're going to come in from negative infinity. Negative infinity. And we are talking about x, so we're going to go all the way to that vertical asymptote, which is negative 1. Our interval stops there, and it picks back up on the other side of negative 1 and continues on the way to infinity. Okay, but x could still be anything. For range, start coming in from negative infinity from the bottom. Always go minimum to maximum. Go all the way up until we have a break and we stop at 0. Then we pick back up on the other side of 0, and then we continue all the way to infinity. Okay, so y could be anything as long as it's not 0. Okay, so these 2 intervals describe this graph. Okay, and there's how we could draw a reciprocal of a linear function. We are going to work with quadratic functions as well, but that will come in a future lesson. Okay, so now let's assume we were given the graph of the reciprocal, and we're asked to actually go backwards and get the graph of the original. Now, keep in mind that we did say that we are going to use the function a over f of x. So a could be some constant, not necessarily 1. So we are going to have to find a way to figure out that constant as well, given the information in the graph. Okay, so let's use this graph they've given to us to graph the linear functions. We do have to draw that linear one as well. So let's start out by finding the vertical asymptote from the graph like we would have before. So if I've got a vertical asymptote, we can see that on my graph, it doesn't look like my reciprocal function goes through x is equal to 2. So that's going to be our vertical asymptote. Now, before, we would have had some expression equal to 0, and we solved for x. Here, it's already solved for x. So let's try to make this equal to 0 to get all the way backwards. It's very similar to quadratics when we use the zeros to find the factors and factors to find the zeros. This is very much so the same thing. This means that x minus 2 has to be equal to 0. So therefore, f of x, my original, has to be x minus 2. That's what's on the bottom, right there. Okay, so that's very important. Now, what we need to do is figure out what this a value is. Now, it says here it's 1. Sometimes it might not say it's 1. It could be some other constant. So we know it's 1 already, because that's what the question tells us. But let's go try to actually come up with a way to find out that it's for sure 1. Now, what you can do is pick a point that's on this reciprocal graph, plug it into here, and we're going to find out if that's actually 1. So let's assume that it's not. Let's assume that y equals a over f of x. Let's put f of x back in. So y equals a over x minus 2. And then we're going to pick a point that we know for sure, like one of those invariant points. That's handy. Okay, that point is at 1, 1. I can clearly see it. We can plug that into here for x and y, solve for what a is. So we're going to let x equal 1, y equal 1, and then we're going to solve for a. So 1 equals a, and this will be 1 minus 2. So 1 equals to a over negative 1. Now that's interesting. We can see that a is actually equal to negative 1. So by doing this, by finding that constant, I now am sure that it's negative 1. Not actually 1. So even though it's still the reciprocal, the constant could change. So it's very helpful to think about this as some constant on top of some function instead of it always being 1, because it might not always be 1. Now that I know that, we can say that y is equal to negative 1 over x minus 2. That is actually the graph of this. If I go to graph the linear function f of x, I'm going to take the bottom part, x minus 2, and graph it. So let's go try and put this in, make sure we do have the same graph. So 1 over x minus 2, and graph. Okay, so it looks good. There it goes through 2. Now if I put in x minus 2, let's see what happens. I'll zoom in a little bit for us. Right over here. Hopefully that, oh, that might not be good. Oh, that's perfect. Okay, so here we go. And wait a sec. Y equals, oh, I put in positive 1. Let me actually put in the negative sign that's supposed to be there. Yeah. Okay, there we go. Now I've got an issue. So let's go back to normal. So if I graph the one that's supposed to be there, we can see that my original doesn't go through those invariant points now. That's interesting. So since that constant's actually negative 1, that negative could also be applied to the bottom. Okay, so I could actually rewrite this as y equals 1 over negative x minus 2. Now notice, now I have the same format as what I was asked to, so use the graph of y equals 1 over f of x. So I've got my 1 on top. My negative just went to the bottom. I didn't really change the value of anything. But now the formats match. I've got a positive 1 on top like I should, and now my negative sign's underneath. So let's go try to fix this. So if I actually put in a negative sign underneath, let's put a negative there. Oh, I need brackets. That's why. So let's just take that out. Negative bracket x minus 2. Now if I graph it. There we go. Okay, now you can see that it goes through those 2 invariant points that it should. So I'm going to zoom in again. Close enough to it. Now I can see them. So I'm going to actually use the intersect function and just double check. So I can go ahead and find an intersection point between the first curve and second curve. And it should tell me that I've got 1, 1, which I do. That's wonderful. So I've got my one invariant point here, which I can see it on the graph. The other one should be at 3, negative 1. So let's do this again. Option 5 is intersect. And we're going to move that cursor, and we're going to move it closer to the other intersection point. So enter, enter, enter. There you go, 3, negative 1, just like our graph says it should be. So just by moving that negative sign down, I actually have the correct function now. So my original function should be f of x equals negative x minus 2. So that'll be the function that actually goes through our reciprocal function where it needs to. Now let's graph it. Now if you learned before how to deal with linear functions, so this is slope-intercept form if I actually distribute the negative sign. So this will be negative x plus 2, which means I've got a negative slope, it's a slope of negative 1, and a y-intercept of positive 2. So my y-intercept is positive 2, my slope is negative 1. So from that point, we're going to go down 1, right 1. Takes me to my invariant point. Do that again, down 1, right 1. Do that one more time, down 1, right 1. So by using the slope and the intercept, we can create that linear function. And you can see that it should go through those 2 invariant points provided when you draw it with your pencil. The slope is correct, and there you have it. It does go through those 2 invariant points that we needed to. Just had to make a little change with where that negative sign actually had to go for that original function. Okay, so there it is. You can see the asymptote right there, and that 2, 0, there is your x-intercept like we predicted. So 2, 0 is my x-intercept. When I do my reciprocal function, it actually becomes the asymptote, the vertical asymptote. Okay, so that is my x equals 2 vertical asymptote. Okay, so we can always use the reciprocal to work backwards to find the originals. Okay, so underneath it just says the graph of y equals f of x is given. Sketch the graph of the reciprocal and write the equation of the vertical asymptote of the graph. Also state the invariant points and the y-intercept of y equals 1 over f of x. Okay, so now we've been given the linear function, and we're asked to actually graph the reciprocated function, the reciprocal of it. So if we go ahead and just start labeling some stuff on here, we should be able to draw the reciprocal. Now, in order to do that, we need to know what the original is. Now, if it is linear, it has a form of mx plus b, slope-intercept form, where m is your slope, b is your y-intercept. And we should be able to fill this in relatively easily by looking at this. So by finding that y-intercept, I'm just going to look right on the graph where it crosses the y-axis, and I can see it's at 1. But then we've got to find the slope. So if you pick 2 points that you know for sure on the graph, and you just count out the rise and the run between them, you can take care of that ratio. So we're going to go up 1 from that point, my x-intercept, go up 1 to get on the same plane as my y-intercept. Now we're going to go over 1, and that's in a positive direction also. So plus 1 again. Now if you remember, anything about slope, it'll be the change in y over the change in x. So 1 over 1, my slope is 1. Okay, so that means my function f of x is equal to x plus 1. Okay, my slope is 1, so I don't really need that coefficient. My y-intercept is 1. You can see it clearly. Okay, so there's my f of x. There's my original. Okay, so that's good. Let's get some invariant points as well. Some invariant points. And we said those were where f of x was equal to positive or negative 1. And those were the 2 points we used. Those were actually the intercepts. So one of those invariant points is negative 1, 0. And the other one is going to be at 0, 1. Okay, those are the coordinates of those 2 points. Okay, those will be my invariant points. Oh, it won't be that one. It's the wrong point. It should actually be one underneath. Sorry about that. So one of my invariant points is 0, 1. That one's good. This one actually just has the wrong x coordinate. So my actual invariant point, I'll do them in pink, should be down here because that's the one on the same level as negative 1. Yeah, my mistake. So 0, 1 is good. The other one should actually be negative 2, negative 1. So negative 2, negative 1. There we go. So those are my 2 invariant points. This is good. I need a vertical asymptote. If I know what the original is, I have enough to find that vertical asymptote. So my vertical asymptote will be from that original function when it's equal to 0. So that means x equals negative 1 will be a vertical asymptote. Okay. So let's add that in there as well. Maybe I'll move these slope markings at that point. So x equals negative 1. This line I'm currently putting in pink dashes. So there's x equals negative 1. I do have my invariant points as well. And now I know where I'm bounded by. Now I should also be bounded by the horizontal asymptote of x equals 0. And we'll move these lines out of the way so we don't have too much going on. There we go. So I am bounded by those 2 asymptotes. I do have my invariant points. Only one way to draw this. Approach the asymptotes from both directions. And there's your reciprocal graph. Okay. Just by looking at that linear function, which you learned about in Math 10, look at all the stuff we can do. We can flip it over. We can state some asymptotes where I can't cross. I have some points that don't change on either graph, and I can draw this out perfectly. And you can even draw them both on here if you want to. So let's do x plus 1, x plus 1, and then our reciprocal graph 1 over x plus 1. And be very careful, make sure you use those brackets. And I gotta zoom out to normal. But you can see that should be 0, 1 right there. That would be this invariant point. So let's zoom 6 this, go back to standard. There's our line. And there's our reciprocal graph. And we can see it. If I zoom in, I might be able to see it a little better. Okay, and there you have it. There's exactly what we've drawn. Okay. Underneath, we are also asked something else. So determine if the graphs of the following functions reciprocal will intersect. So I've got 2 functions. I need to determine if their reciprocals are going to meet, and if so, we can also find out where. Now let's just take the reciprocals of these first. If we take the reciprocals, one of them is going to be x plus 2. The other one is going to be negative x plus 2, just by flipping the numerator denominators places. Now, if these graphs intersect, that means there's a point, there might even be more than one point, where these 2 have the same values. Now, since these are linear, they will only have one point of intersection. Now, if they do cross, that means there's a point where they're equal. So if I have 2 expressions for y, I know that whatever y is equal to should be equal to each other. So x plus 2 is going to be equal to negative x plus 2. If they cross, this equality will hold true, and there's going to be a number we're going to find. If it doesn't work, that means they don't intersect. So let's find out if this works or not. So collecting like terms, if I add an x to both sides, that means that 2x plus 2 is equal to 2. If you minus 2 from the left, that means 2x is equal to 0, so x is equal to 0. So by finding that, we now know that there's an x value where these two are equal. We can go find the corresponding y value as well. If we were to plug that in to those reciprocal functions, we're going to find the y values that they're equal to. So if y is equal to 0 plus 2, that means y is equal to 2. You can try out the other one as well, but it should give you the same thing since we use them both to find x, but you can do it anyways. So negative 0 plus 2, which is really just 2. So there's a point on the reciprocal graphs where they cross. That also means there's a point on the original where they cross. So we can say, so therefore, the reciprocals will cross at 0, 2, but the originals will cross at 0, 1/2. Okay, remember how the reciprocal works. I am taking those values of y and flipping them, the reciprocal. So if the originals cross at 0, 1/2, the reciprocals cross at 0, 2, the flipped version of that y value. Okay, you could graph them as well and find those intersection points for yourself. Desmos is a great tool to do this really fast, but this calculator will work as well. It just takes a little bit more time. So yes, these reciprocal functions will intersect, and they will intersect at 0, 2. Okay, on the back, you've got a little bit of a summary of everything we talked about. So you can see reciprocal functions can be represented by transforming f of x to 1 over f of x. When this occurs, your x-intercepts become non-permissible values. You have all of this information here. It even gives you a completed graph with all of the things we've talked about and how they found them. You even have one more. When solving for reciprocal functions based on the graph, determine the vertical asymptote, then use an invariant point to solve for the coefficient. So there's that a value we talked about again, because again, it could be 1, could be 2, could even be negative, and we saw a little bit of an issue that created for us, but nothing we couldn't handle. So there's that first lesson. When I see you again, we're going to talk about graphing quadratic reciprocals. So we only dealt with linear functions in this one. When I see you again, we'll deal with quadratics as well. So just be aware that that's coming. And again, if you do need some extra help, please ask your teacher, send me an email as well. I'll be more than happy to help. So take care, and we'll see you in the next one.